This technology called Tcsql is a new kind of technology featuring the following capabilities. First of all, it features the ability to do graph management. In particular, the maintenance of this thing called transitive closure. It features the notion of something called soft schema, which provides the ability to support object-oriented programming directly in a relational database system, complete with notions of classes and objects and single and multiple inheritance and polymorphism, and a collection of other capabilities on top of these two basic capabilities. We're going to start by doing a little graph theory here. In front of us are two graphs, a family tree and a graph of bus routes. Some of the components of a graph consist of the following: the notion of something called nodes. In this family tree graph, the nodes happen to be the names of people here. A second component of graphs are these things called connections here, or edges. And they happen to be the arrows we see between nodes here. Sometimes in graphs, you have a semantic relationship associated with these arrows. In this family tree graph, we have a father of relationship, and we have a mother of relationship. Sometimes with graphs, you have scalar values associated with the connections. In this bus routes example, the scalar value represents a cost of going from one city to another. The notion of transitive closure is a concept that is foreign to most people. So let's look at a definition of transitive closure. Given a graph G, the transitive closure of a graph is the set of all potential paths between all nodes in the graph here. So in fact, the transitive closure of a graph can be represented using a relational table here. So the way to think of the population of this table, you can think of it as follows. Take any two nodes in the graph, let's say starting with N1 and looking at N6. Does there exist a path, directed path from N1 to N6? The answer is yes. Therefore, we see a transitive closure record here. Does there exist a directed path from N2 to N6? Notice I say the word directed, you got to follow the directions of the arrows. The answer is no. So N2, N6 does not show up here. So what can you do with the transitive closure of a graph? You can use it to navigate a graph. So if we want to know all of the descendants of N1, what we can do is write a select statement as follows. Select child from transitive closure where parent equal N1. Now let's play computer a second here and let's execute this query here. Let's find all the rows here where the parent has a value of N1. We see that in green here. And let's find all of the children from all those records. And what we find is we get N2, N3, N4, and 5, N6. So in fact, that represents all of the descendants of N1 here. Now, one of the unique things about transitive closure with respect to Tcsql features the ability to maintain transitive closure in a graph as a graph changes. So normally, if you're adding or deleting nodes or connections in the graph, what happens is you typically have to rederive the transitive closure from scratch. One of the features of Tcsql is its ability to maintain transitive closure whenever nodes or connections are added or deleted from a graph. The object-oriented paradigm can be represented as a graph problem. So here we have a class here called class 1, which has properties A, B, and C, and a hazard relationship between the class definition and its associated properties. We also have another class here called class 1.1 with properties D and E. And we see a relationship here between these two nodes, an is-a relationship, meaning that class 1.1 is a specialization of class 1. Now let's look at a graph here. Let's look at what happens if we want to instantiate class 1.1. Let's look at the equivalent object graph. In this case, it would look like the following. Assuming we want to instantiate class 1.1 and we're going to call that object 1, what happens is the following. We first want to instantiate properties D and E, and then we want to look at this inheritance is-a link here to inherit properties A, B, and C, which is what you see down here. Okay, now let's look at the relational tables needed to support this paradigm here. So we have the notion of a class table here, which represents the nodes of our class graph here. It's basically a name-value pair here, and we have a type column here. and legal type values. This represents basic class types here. We have a class connection table of parent-child nodes here and a connection type here. In this case, it's going to be either has-a or is-a. And then we have a transitive closure table representing the transitive closure of this class graph. And assume for a minute that this transitive closure table is automatically populated and managed whenever nodes or connections are added or deleted in this class graph. Let's look at the tables needed to support our object graph here. We have a table called object, which represents the nodes of our object graph here. Again, it is basically a name-value pair with a class column here representing the kind of class that we're instantiating here, including the class properties. We also have an object connection table here, which represents the connections of our object graph. So it's a parent-child pair, again with connection type. And we have a transitive closure table associated with our object graph. And assume here also that this transitive closure table is maintained automatically whenever nodes or connections are added or deleted in our object graph here. So this whole paradigm here I'm describing here with these 6 relational database tables is something known as a soft schema. In the last slide, I introduced the notion of a soft schema. So let's look at the difference between this thing called a soft schema and a normal, what I would call a hard schema. So here's a conventional relational table, a customer table with 3 columns, full name, phone, and product. I claim this can be represented as a class graph as follows. So we have the name in the table here called customer and the 3 columns indicated here. Relational tables associated with a soft schema equivalent look like the following here. So we have a class table here. Notice this first record here is has-a of type connection. So even the connection type here is shown here as a row in the class table. Now we have the name of the table here, customer, and the 3 column names here, which show up here as records as well. We also have the class connection table. I should point out here that in this slide here, we're showing the class table as having an ID field, which uniquely identifies the row here. This actually more accurately represents the true implementation here. So our class connection table is really ID values here. So we have a parent and child ID columns and a connection type here. We see a value 3, which is a has-a. Now that represents the schema for the table here. Let's look at the equivalent object graph here representing the actual data in the table here. So we have a row here. So we have a customer record here which has 3 fields, full name, phone, and product. And now we see the values filled in for these particular graph nodes here. So let's look at the soft schema tables associated with the object graph here. So we have an object table here, and now we have the name value pairs that you see reflecting this graph here. And we have an object connection table here representing these connections here. So what I've shown here is that the information that you would normally see in a hard schema here, its equivalent in a soft schema is reflected here. Now what happens if we were to add another conventional hard schema table here? So we have a supplier table here with columns company and vehicle here. What changes over here now? Well, first of all, we add new rows here in the class table representing the supplier table and columns company and vehicle. And we would also have equivalent appropriate rows populated in our class connection table. Representing the actual data of this supplier table here, we have records added in the object table here. Here's our name value pairs, and appropriate records added to the object connection table. I did not bother showing the transitive closure tables here. The thing to point out here is that every time we add a new table, what you would normally see in a hard schema, there are no tables added in our soft schema here. The only thing that are added are new rows to these existing tables that you see here. And so it is by this approach we're able to take a conventional approach of a hard schema that may entail possibly tens of thousands of tables and do the equivalent with this notion of a soft schema representing what you see here, 4 tables plus the 2 additional transitive closure tables. With this soft scheme model, let's look at an example of instantiating a class instance here. So we have a class graph here, and all the data in this graph can be represented with 2 tables here. So we have a class table representing all of the nodes of this graph. We have a class connection table showing all of the connections here. Now I didn't bother showing all of them. I just showed a few of the rows here. Okay, now let's look at what happens when we want to instantiate this particular node here, a boy. What we're going to do is instantiate this boy. We're going to call this instantiation Andy here. And what is going to happen behind the scenes is Tcsql is going to figure out all of the particular properties that need to be inherited here, and it will populate appropriate object and object connection tables here. And these 2 tables will represent an object graph that looks like the following here. Notice here that I've introduced a new kind of relationship, a has-not relationship. Tcsql supports the ability to do inheritance override here. Now, if you were to implement this in an object-oriented language such as C# or Java, this is the object graph equivalent what you would get here. Now, the real power and beauty here is I did this directly in a relational database using standard SQL. Let's look at how to apply the Tcsql capabilities talked about in the previous slides toward developing a process/project management application. So imagine the following here. We have a house that we want to build, and the house is broken down into first floor and second floor, broken down into various rooms. And so what we're going to utilize here is the notion of a work breakdown structure. And each work breakdown structure node is broken down into smaller chunks of work here, as you see. And assume that at each level of abstraction here, there's a number of attributes associated with that level of abstraction, namely a collection of tasks that must be accomplished, and assume there's a temporal relationship between the tasks. And so, in effect, what we're going to be constructing is a little mini task network associated for each level here. So let's now define a process for creating a house. So we'll start out with the notion of a house entity. So this will become a record in the class table. We have the notion of a floor and a connection between the two, a work breakdown structure connection. A floor will be broken down into 1 or more rooms here, so these are all records in our class table here. We'll introduce the notion of a task here. And the task will have a property, it has a property. In this case, it's called estimated duration. A second property called actual duration. And we'll introduce a new kind of connection here called a temporal connection here. And here we're doing something different, something we haven't seen in any other presentation. We're going to introduce an attribute associated with a connection called delay. And we're going to introduce an entity here called T9, which turns out to be, it's an is a relationship, so T9 is a task. Similarly, we're introducing this thing called T10, and T10 is a task. And we're going to create a temporal relationship between T9 and T10, meaning in order to start task T10, T9 must first complete. Now we want to connect T9 as a task of part of this higher level entity called a room. So we have has a relationship here. Similarly, we're going to connect T10 as a has a property of room here. So now we defined a room here. So we will do something similar with defining a floor, and continuing we will do something similar with defining the tasks associated with this entity called a house. Okay, let's now look at our finished process definition here So in the last slide, you saw we were putting together a definition of a room, which had tasks T9 and T10, and the temporal relationship between them. So here's our floor definition, and here's our definition for our higher level entity called a house here. And notice that here we have a task called T1.1, which is a specialization of a more general task called T1. Similarly, we have task 3.1, which is a specialization of a more general task called T3. And we have this temporal relationship here between these general tasks here. Notice also that we have temporal relationships between tasks that cross entity boundaries here. So let's assume now we would like to create a project plan by instantiating our process definition. So let's assume we would first like to instantiate our house entity here, and we're going to call this instance my house. So the name is my of type house. And what Tcsql will do behind the scenes is instantiate all of the tasks that define our house entity here. Notice though that what appears in this circle here is slightly different than what appears in our template here because of the following. In our template definition, we had this temporal relationship between these general tasks here. Well, what happened when we instantiated this entity is Tcsql was smart enough to realize that there needs to be this behavior inherited between these two tasks. So now we have a temporal relationship between task T1.1 and task T3.1. Let's assume now we would like to instantiate a floor, and we're going to call it first. So we insert into our object table, naming it first of type floor. And Tcsql behind the scenes will instantiate our tasks here and the temporal relationships between them. Assume now we would like to connect our first floor to our house here. So we're going to insert into our object connection table. And what Tcsql will do behind the scenes is connect up the tasks that cross entity boundaries here, this temporal relationship here. Continuing, let's assume we would like to instantiate a room, and let's call it a kitchen. So here we're inserting into our object table again, calling it kitchen of type room. And again, Tcsql behind the scenes will instantiate our tasks here and create a temporal relationship. Let's assume we would like to connect our kitchen to our first floor here. So we insert into our object connection table. And again, Tcsql behind the scenes will connect our tasks that cross entity boundaries here. Now look what we have accomplished here. In a mere 1, 2, 3, 4, 5 insert statements in the appropriate tables, we've instantiated a project here. We've instantiated our process definition here. So we've in fact introduced a new paradigm, a very powerful way of defining and instantiating a project plan. To begin, let's look at a database table you might find in an electronic healthcare record system for healthcare. So something that looks like the following: a column of names, a column of visit dates, and a column of diagnoses. Now, with such a table, this is a table you'd find in an information system. There are certain questions you might want to ask. You might want to ask, tell me all the patients here that have ulcerative colitis. So you can write a select statement that basically is looking in the fact column here for something called ulcerative colitis, right there. You might ask, anyone here have Crohn's disease? Again, you can write a select statement specifying where fact equal Crohn's disease. We see such a patient there. What if we wanted to ask, find all patients that have a digestive system disease? Well, you'll notice in our fact column here, there is no value that says digestive system diseases here. And so what you would have to do instead is write a select statement and then include a comma-separated list of things that constitute a digestive system disease, ulcerative colitis and Crohn's disease. What if I want to ask patients who have an autoimmune disease? Well, again, that ends up being a comma-separated list. I have no idea what that looks like. But the problem here is that in these higher level kinds of questions, in order to answer them, given simply an information system, I have to have a hard-coded list of legal values. Let's look at the difference between data versus information versus knowledge. If I showed you the following, would you consider this to be data or information or knowledge? Well, it turns out it's just data. And the reason why is because you look at this and it looks like a column of names. That's because it is something you recognize. This looks like a column of diseases. That's because you're familiar with it. But by itself, it is merely data, just text strings. Now, if I add column headers here, these column headers are what are known as metadata. And so what we get is data here plus metadata is our definition of information. Well, what if I take and put an overlay here, the following? We see type 1 and type 2 diabetes are specializations of this more general category of diabetes. Ulcerative colitis and Crohn's disease are specializations of this more general category called digestive diseases. So what do you call this structure here, this knowledge overlay? I call it meta-information. And so my definition of knowledge is information plus meta-information. This knowledge overlay here is something called an ontology here. There are semantic relationships between the nodes here. And what this allows you to do is the following. If you view this as a relational table here, you can certainly ask questions about who has type 1 diabetes in your database here. What an ontology overlay allows you to do is ask higher level questions. Tell me all the people in my system that have diabetes in general or have autoimmune diseases in general. In this example, we're going to do the following query. Find all diabetes patients here. So at the top here, we have a graph, something called an ontology, where you have a semantic relationship between nodes here. In this case, it's an is-a relationship here. At the bottom, we have a standard relational table, an electronic healthcare record table here with patient information. And so the query looks like the following select statement here. And what we're going to do is we're going to play computer and run through step by step what happens in executing this query. In the first part here, we have a where transitive closure patient is diabetes. So we show that here. And what we're going to do is look at all of the children, in other words, all the descendants in the transitive closure table here. So that shows up in purple here, all the descendants of diabetes. And then what we're going to do is a join on the electronic healthcare record table here, where the fact value corresponds to the descendant value here of the transitive closure. And then we're going to return here the select e.patient. We're going to return the patient column information here in the result here. Now this query is an example of a query type called a subsumption query. So let's look at an example that further illustrates the difference between an information system and a knowledge system. So we're going to look at a healthcare example, the notion of diabetes mellitus. So in an information system, such as an electronic healthcare records system, you can ask queries that are specific with regard to diabetes mellitus. Tell me all patients in the hospital that have diabetes mellitus. When you take your information system and overlay it with a set of ontologies, you get a much richer set of questions you can ask it. So for example, with this notion of diabetes mellitus, we can return a set of medical devices associated with it, genes associated with it, body parts associated with it, diagnosis procedures, lab procedures, so on and so forth. You get the idea. Let's look at a Holy Grail of IT example, something that would be very difficult to do with a search engine such as Google. Imagine you wish to determine how many people in Illinois have an autoimmune disease. Imagine you have a graphic such as the following that shows the United States broken down into regions, regions broken down into states, states broken down into counties, counties broken down into cities, and at the leaf nodes, the names of healthcare institutions. Imagine being able to do the following. Imagine being able to take your query and to drag and drop it into a box, and to have that query request propagated to all of the descendant nodes, and then being able to execute and aggregate the results together. Now this would be very difficult to do with a search engine such as Google for the following reason. In order to execute such a query, someone would have had to do that analysis in advance and then take that result and publish it in a text document. Only then would it be possible to execute such a query in a search engine such as Google.